Let's now turn our attention to the practical applications of machine learning, where these powerful techniques are already transforming industries and creating value in the real world. The versatility of machine learning is truly remarkable, with meaningful applications across virtually every sector of the economy. Let me share some compelling examples from diverse domains. In marketing, machine learning has revolutionized how companies understand and retain their customers. Predictive models can identify which customers are at risk of churning, allowing for targeted intervention before they leave. Customer lifetime value models go further, helping businesses identify their most valuable long-term relationships and allocate resources accordingly. These capabilities transform marketing from gut feel decisions to data-driven strategy. Social media platforms leverage machine learning for sentiment analysis, automatically gauging public opinion about brands, products, or events by analyzing millions of posts in real time. This provides businesses with unprecedented insight into how customers perceive them and allows for rapid response to emerging issues. Automation represents another frontier where machine learning is making extraordinary advances. Internet of Things devices generate massive data streams that machine learning algorithms can analyze to optimize everything from energy usage in buildings to preventive maintenance in factories. Drones equipped with computer vision can inspect infrastructure, monitor crops, or deliver packages, all guided by machine learning systems that continuously improve their performance. In healthcare, machine learning is quite literally saving lives. Algorithms can now predict disease outbreaks, identify patients at risk for complications, and detect early signs of conditions like cancer or heart disease in medical images. These capabilities enable earlier interventions and more personalized treatment approaches, improving outcomes while potentially reducing costs. The insurance industry has embraced machine learning to transform risk assessment and claims processing. Predictive models evaluate factors that traditional actuarial methods might miss, leading to more accurate pricing. When claims are filed, machine learning systems can rapidly assess validity, detect potential fraud, and streamline the settlement process. Sales and e-commerce have been revolutionized by recommender systems, machine learning algorithms that analyze your past behavior to suggest products you're likely to want. These systems drive significant revenue for online retailers while simultaneously improving customer experience by helping people discover relevant products. Perhaps no application better illustrates the value of machine learning than fraud detection. Credit card companies analyze billions of transactions in real time, using sophisticated algorithms to identify potentially fraudulent activity with remarkable accuracy. This protects both financial institutions and consumers, while allowing legitimate transactions to proceed without interruption. What makes these applications so powerful is that machine learning systems improve over time as they encounter more data. A fraud detection system that flags an unusual transaction today becomes more precise tomorrow when it learns whether that transaction was actually fraudulent. This creates a virtuous cycle where better data leads to better models, which generate more value, which attracts more data. As computing power increases and algorithms become more sophisticated, we can expect machine learning to expand into new domains and tackle increasingly complex problems, continuing to transform how we work, how we make decisions, and how we solve some of society's most pressing challenges. As we consider implementing machine learning solutions, let's discuss the programming languages that power these technologies. Several languages have emerged as the tools of choice for machine learning practitioners, each with its own strengths and characteristics. 4 languages in particular dominate the machine learning landscape: R, Python, Java, and MATLAB. While all can be effective, there are significant differences that influence which is most appropriate for specific applications. Python has emerged as perhaps the most popular language for machine learning today. Its rise to prominence isn't accidental. Python combines remarkable versatility with accessibility. As an open-source language, Python benefits from a vibrant community that has developed comprehensive libraries specifically for data science and machine learning, including NumPy, Pandas, scikit-learn, and TensorFlow. The beauty of Python lies in its readability and relatively gentle learning curve. Even people without extensive programming backgrounds can become productive quickly. This accessibility doesn't come at the expense of power. Python scales effectively from simple analyses to complex deep learning implementations. R, like Python, is open source and has a strong following, particularly among statisticians and researchers. Originally designed specifically for statistical computing, R excels at data visualization and exploration. Its specialized packages for statistical modeling make it particularly well suited for certain types of analysis. Both Python and R have gained prominence partly because they're dynamic languages, allowing for rapid iteration and experimentation. Crucial capabilities when developing machine learning models that often require extensive fine-tuning. The open-source nature of these languages brings significant advantages beyond just cost savings. It means continuous improvement from global communities of contributors, extensive documentation, and readily available support through active forums and discussion groups. Another key advantage of Python in particular is its versatility beyond machine learning. The same language used to build your predictive models can also power your web applications, mobile development, or automation scripts. This reduces the translation layer between model development and deployment, streamlining the path from concept to production. Java remains important in enterprise environments where integration with existing systems is crucial. While perhaps not as nimble for exploratory data analysis, Java's performance characteristics and strong typing make it valuable for deploying models at scale. MATLAB, with its commercial licensing model, occupies a different niche. Its specialized focus on mathematical operations and strong visualization capabilities make it particularly useful in academic and research settings, especially for certain specialized applications. Let me now highlight why R has earned its place as one of the premier languages for machine learning and data science. First and foremost, R is completely open source and free to use. This accessibility removes financial barriers to entry, making powerful data analysis capabilities available to everyone from individual researchers to large enterprises. The open source nature also means R benefits from contributions by thousands of statisticians, data scientists, and developers worldwide who continuously enhance its capabilities. R combines both object-oriented and functional programming paradigms, offering remarkable flexibility in how you approach problems. This dual nature allows R to accommodate different programming styles and preferences, making it adaptable to various analytical challenges. Whether you prefer the clean, modular approach of functional programming or the structured organization of object-oriented code, R supports your workflow. One of R's most appealing features is its extensive collection of built-in functions that dramatically simplify data manipulation and exploration. Functions like head and tail let you quickly examine the beginning or end of your dataset. These seemingly simple tools save countless hours when working with large datasets, allowing analysts to gain immediate insight into their data structure without complex coding. R's sophisticated capabilities extend far beyond basic data manipulation. As a Turing-complete language, R can theoretically solve any computational problem given sufficient resources. This enables R to handle complex tasks like natural language processing, where algorithms analyze and interpret human language. From sentiment analysis of customer reviews to topic modeling of research papers, R provides the tools to extract meaning from text data. The language's statistical heritage gives it particular strengths in areas requiring rigorous statistical analysis. R was built by statisticians for statistical computing, and this DNA remains evident in its comprehensive implementation of statistical methods, from basic descriptive statistics to advanced modeling techniques. R's visualization capabilities deserve special mention. Packages like ggplot2 have revolutionized data visualization, making it possible to create publication-quality graphics with relatively simple code. These visualizations aren't just aesthetically pleasing, they're powerful tools for understanding complex relationships in data and communicating insights effectively. The R ecosystem now includes over 18,000 packages on CRAN, the comprehensive R archive network, covering virtually every conceivable analytical need. From specialized packages for genomic research to financial analysis tools, the R community has likely already built and shared solutions relevant to your specific domain. For machine learning specifically, packages like Caret provide unified interfaces to dozens of algorithms, while Tidy Models offers a cohesive framework for model building. These tools streamline the path from raw data to deployed models, making sophisticated machine learning accessible even to those without extensive programming backgrounds. While R may have a steeper initial learning curve than some alternatives, the investment pays significant dividends through R's expressive power and analytical capabilities. In the hands of a skilled practitioner, R transforms from a programming language into a versatile instrument for data exploration and discovery. Let's conclude by walking through the fundamental process of developing a machine learning solution, a roadmap that applies regardless of which approach or programming language you choose. The machine learning journey begins by clearly defining the problem you want to solve. This crucial first step requires translating business challenges into precise questions that machine learning can address. Are you trying to predict which customers might cancel their subscription? Identify fraudulent transactions? Optimize pricing? The clarity of your target problem directly influences every subsequent decision in the process. Once your objective is clear, data collection and preparation become the foundation of your project. This phase, often called data wrangling, typically consumes 60 to 80% of the total project time. It involves gathering relevant data from various sources, cleaning it to address missing values and errors, transforming variables into suitable formats, and engineering features that help the algorithm learn effectively. The quality of your data preparation largely determines the potential success of your model. With prepared data in hand, you'll train your algorithm, allowing it to learn patterns from historical examples. This is where your machine learning algorithm begins to develop its predictive capabilities. During training, the algorithm examines your data, identifying relationships between inputs and outputs, or discovering inherent structures. The algorithm progressively refines its internal parameters to capture these patterns as effectively as possible. However, a model that performs well on training data isn't necessarily valuable in practice. The critical next step is testing your algorithm on data it hasn't seen before. By setting aside a portion of your data specifically for testing, you can evaluate how well your model generalizes to new situations, the true measure of its practical utility. This testing phase serves as a reality check, helping you avoid the pitfall of creating models that merely memorize historical data rather than learning transferable patterns. Finally, you'll evaluate your results against appropriate metrics. For classification problems, you might focus on accuracy, precision, recall, or F1 score. Regression models might be evaluated using mean squared error or R squared. The choice of evaluation metric should align with your business objectives. A fraud detection system that prioritizes catching all fraudulent transactions might optimize for different metrics than one focused on minimizing false positives. Throughout this process, the distinction between training and testing data is absolutely fundamental. Your training data teaches the algorithm, while your testing data validates its performance. Without this separation, you risk creating models that appear successful but fail when deployed in real-world settings. It's also important to recognize that machine learning development is rarely a linear process. You'll likely cycle through these steps multiple times, refining your approach based on results. You might collect additional data, engineer new features, try different algorithms, or adjust parameters to improve performance. The ultimate goal isn't perfect accuracy. It's creating a model that delivers meaningful value for your specific business problem. A model that achieves 85% accuracy but addresses a critical business need effectively may be far more valuable than one with 95% accuracy on a less important task. Now that we understand the fundamentals of machine learning and why R is such a powerful tool for this work, let's get practical and explore how to set up your environment with RStudio. Getting started with R and RStudio is straightforward. First, you'll need to download and install R itself, the core programming language and computational engine. Visit CRAN, the Comprehensive R Archive Network, at r-project.org and select the version appropriate for your operating system, Windows, Mac, or Linux. After installing R, I strongly recommend downloading RStudio, which serves as an integrated development environment or IDE for R. While you can use R without RStudio, the IDE provides a much more user-friendly and productive experience. Visit rstudio.com/product/rstudio/download and select the free desktop version. Install it just like any other application on your system. When you launch RStudio for the first time, you'll be greeted by an interface divided into 4 main panels, each serving a distinct purpose in your workflow. In the top left, you'll find the script pane. This is where you'll write, edit, and save your R code. Think of this as your document workspace. Code written here isn't executed automatically, allowing you to develop and refine your analysis before running it. When you're ready to run your code, you can execute selected lines or the entire script. The bottom left contains the console. This is where code is actually executed and where results appear. You can type commands directly into the console for immediate execution, which is useful for quick calculations or exploring data interactively. When you run code from your script, it's also executed in this console. The top right holds the environment and history panes. The environment tab shows you all objects currently in memory, your datasets, variables, and functions. This gives you a clear overview of what you're working with at any moment. The History tab keeps track of commands you've previously run, making it easy to recall and reuse code. Finally, the bottom right contains multiple useful tabs including Files, Plots, Packages, and Help. The Plots tab is where your visualizations will appear when you create graphs. The Packages tab helps you manage R's extensive library of add-on packages. The Help tab provides documentation and examples for R functions. Let's briefly touch on some basic R syntax to get you started. In R, you assign values to variables using the assignment operator, which looks like an arrow. For example, x10 assigns the value 10 to the variable x. While you can also use the equals sign for assignment, the arrow is the conventional choice in R programming. Functions in R are called by their name followed by parentheses containing any arguments. For example, mean, 1, 2, 3, calculates the average of the values 1, 2, and 3. The CE function here creates a vector combining these values. R is particularly powerful for data manipulation. The function read.csv, filename.csv, imports data from a CSV file, while functions like head and tail let you peek at the first or last few rows of your dataset. Basic operations are intuitive: plus, minus, asterisk, and / work as expected for arithmetic. Logical comparisons use familiar operators like double equals for equality, exclamation mark equals for inequality, and less than, greater than, less than, or equals, greater than, or equals for comparisons. As you begin working with RStudio, remember that the help system is your friend. Typing * followed by the function name in the console will bring up detailed documentation for any function, complete with examples of its use. With RStudio set up and these basic commands in mind, you're ready to begin your journey into data analysis and machine learning with R. The environment you've just established provides all the tools you need to progress from simple data exploration to sophisticated predictive modeling. As we conclude our exploration of machine learning and R, let's discuss the path forward for those of you eager to deepen your understanding and build practical skills. If you're new to R, your immediate focus should be on mastering the language's fundamental data structures and operations. This foundation is essential before diving into complex machine learning algorithms. Without a solid grasp of how R handles and manipulates data, even the most sophisticated machine learning techniques will remain challenging to implement effectively. Start by familiarizing yourself with R's basic data structures: vectors, matrices, data frames, lists, and factors. Each serves a distinct purpose in the data analysis workflow. Vectors store sequences of values of the same type, while matrices organize data in two-dimensional arrays. Data frames, R's most commonly used structure for analytical work, resemble spreadsheets with rows and columns of potentially different types. Lists offer versatile containers for diverse data types, and factors efficiently store categorical variables. Once comfortable with these structures, invest time in learning R's data manipulation capabilities. Functions for subsetting, filtering, transforming, and aggregating data will become the tools you use daily. The dplyr and tidyr packages, part of the tidyverse collection, provide especially intuitive and powerful functions for these operations. Practice importing data from various sources: CSV files, Excel spreadsheets, databases, and web APIs. Real-world machine learning projects rarely begin with perfectly formatted data in your workspace. You'll need to bring it in from somewhere. As you build confidence with data manipulation, gradually introduce yourself to exploratory data analysis and visualization using ggplot2. The ability to visually explore your data is invaluable for understanding patterns, identifying issues, and communicating insights. Only after establishing this foundation should you begin exploring machine learning algorithms in R. Start with straightforward techniques like linear regression and basic classification before progressing to more complex approaches. Packages like Caret and Tidy models provide accessible frameworks for implementing these methods. Remember that the journey of learning R for machine learning is incremental. Each concept builds upon previous ones, and rushing ahead often leads to confusion. Be patient with yourself, practice regularly with real data sets, and celebrate your progress as you gradually expand your capabilities. The investment you make in learning R's data structures and operations will pay dividends not just in machine learning, but across the entire spectrum of data analysis. These fundamental skills transfer to virtually every analytical challenge you'll encounter, forming the bedrock of your capabilities as a data professional. Thank you for your attention throughout this presentation. The world of machine learning offers endless opportunities for exploration and innovation, and I wish you success as you continue your learning journey.